Right, hello everyone. Welcome to the second last talk of the term in the year. Just a reminder for you to please wear your mask while you're in the audience. Tonight we are very honored to have Dr. Anastasia Fialkov with us to give a talk titled Mysterious Fast Radio Burst. Before we begin, here's an introduction of our speaker. Dr. Anastasia Fialkov's research interest spans from the dark ages to the present days, including astrophysics and cosmology, with the 21 cm line of neutral hydrogen, intensity mapping of other molecular and atomic lines, structural formation, nature of dark matter, transient phenomena such as fast radio bursts, and low-frequency radio observations and instrumentation. She obtained her BSc in physics and BA in electrical engineering from Technion, Haifa, Israel, and her MSc and PhD in physics from Tel Aviv University in Israel. She was a senior Kavli fellow at the Institute of Astronomy and Kavli Institute for Cosmology in Cambridge, and is currently the Royal Society University Fellow, Research Fellow at Sussex University. Sorry.
I'm here at Cambridge as a lecturer now.
Right, sorry, yeah. Right, sorry about that. Dr. Anastasia Fialkov is the lecturer at Cambridge. Now, without further ado, Dr. Anastasia Fialkov, please.
Thank you. Thank you very much for coming, for the people online on Zoom. So I'll be talking about fast radio bursts. Do you know how to remove this bar?
Add more. Can you go to more?
More.
Yeah.
Right. So I was talking about fast radio bursts. Who in the audience has heard about fast radio bursts? Okay, good. So fast radio bursts are still unknown. We don't know what creates them, and that's still a mystery despite the current observational effort and the really success of some telescopes in probing them. So I'll be giving you first a very broad introduction. It's a public talk, so into this history of discovery of fast radio bursts, what they are, how they are characterized, and then I'll show you some of the latest results, and also what are the implications of fast radio bursts for our understanding of the universe, such as cosmology. Okay, so this is a brief summary of facts about fast radio bursts. So the new type of radio sources that were only recently discovered. So the first one was discovered in 2001 by digging through archival data of Parkes radio telescope, and then it was only published in 2007. So several years later after the discovery, because scientists were not sure what it is and how to explain it. It was just a mysterious spike in their radio data, and they didn't know if it's astrophysical or artificial in nature. So it took many years to verify the discovery, and after they were confident in its astrophysical nature, they eventually published it. So at present, there are many of them detected at rate of thousands per sky per day. So if you take the entire sky and count how many radio bursts we receive, it's around 1,000. So it's a very large number. And they are in their nature very short, so 1 or a few milliseconds. So extremely short, extremely bright pulses of energy emitted in radio. So it's just around 1.4 gigahertz to 100 megahertz, so really low radio frequencies. Okay. Now we know that most of them are propagated through the cosmic time and come to us from very distant universe, and I will explain in this talk how do we know that exactly. But by now we are confident that most of them are coming from very far in cosmic history, and therefore they can tell us by their nature, by how they look like, they can tell the story of the universe evolving through this cosmic time. Okay. And it's been shown by data that most of them are not repeating. So we observe one flare from one galaxy at a time, but some of them amazingly were found to repeat. So there are only 18 sources out of 1,000 known that repeat. And the repetitions are non-periodic, so only 2 out of these sources are found to be periodic. So sometimes periods are a few days, or it can be 100 days or so. But most of them repeat sporadically. So there is a burst of flares from the source, and then it goes quiet, and then another time there is another group of bursts. But actually, there's only around 20 of repeating FRBs, while most of them, out of the few hundreds known today, are non-repeating, at least apparently. So these are just brief summary of facts that we know today about fast radio bursts. And let's see more in detail what can we learn and what they are. So this is how a detection of the first radio burst looks like. Sorry for the quality of the picture. And it was detected by Parkes radio telescope in Western Australia. It's a 64-meter dish, very sensitive radio telescope located not far from Sydney. And what you see on this, what is called waterfall plot, is the frequency versus arrival time of the pulse. This here and these are the noise, and this white line here is the pulse itself. So we see that it arrives to the telescope at different frequencies and at different times, and this is called dispersion of the pulse, because imagine it is produced at the same time as the source, but then it is changed by the medium through which it propagates in such a way that lower frequencies will here arrive earlier, while higher frequencies arrive later. So this is called dispersion of the pulse, and that's what scientists saw in their raw data. So if you just plot it, so flux is how strong the pulse is in radio versus time, it looks like a tiny blink, and it's a duration of few milliseconds. So it's like a blink of an eye, basically. So this pulse was identified to come from Magellanic clouds and was found by Professor Duncan Lorimer, who's a professor at Western Virginia, and he's actively working today as well on detecting and understanding fast radio bursts. So this burst is very bright, even compared to the known burst today, and it is 60 billion times stronger than the emission from the sun. So it's much brighter than the sun, 16 billion times. It's a lot. So this is a very energetic phenomenon. We don't know what creates it, and even the energy of it is comparable to the explosion of a full star in supernovae, but emitted in a very short time. So at first, though, the community was very skeptical even when they published this first paper, because such radio telescopes are very sensitive to the point that even microwaves at radio observatories are kept in what is called Faraday cage. So they are behind bars which prevent electromagnetic waves leaking out. And so if you put the microwave inside such a case, a nearby telescope will not see it. But if it's not in a cage, if you open and close the door, because there is magnetic field inside, it creates spikes in electromagnetic field, and this can be detected actually by radio telescopes. This is a telescope at Jordan Bank, close to Manchester. So you can actually go visit. They have a very nice visitor center there. And so because the scientific community was not sure about the nature of the sources, they were first thought to be artificial and called peritons, which is this mythological animal, a deer with wings. So most people thought that it was just an artificial signal that is not cosmological in origin. But then a very interesting event happened in 2013. Thornton et al. They found another burst by using a different telescope. So using this telescope that is called Arecibo, and it's a big dish located in Puerto Rico of 300 meters. So unfortunately, this telescope died recently, one of the cables broke, and this receiver fell into the dish, and it just doesn't exist anymore, unfortunately. But it was fundamental for this field because with this telescope, which is much more sensitive than Parkes, another radio burst was discovered. So it was a completely different source located in a different part of the sky. And it was also found to be repeating. So this 1102 fast radio burst detected by Arecibo actually has been monitored since then by many telescopes in the world and many different regimes, so X-rays and UV and everything that one wants. So it allowed properties of this fast radio burst and its host galaxy where the source is coming from to be very well studied. So, but this detection of another fast radio burst that can be much better studied than the one detected by Parkes, which was one-off event, allowed the scientific community to actually believe in that fast radio bursts are of astrophysical origin and not from microwaves. So nowadays there are many telescopes. The most sensitive radio telescopes in the world are looking for this fast radio bursts because they're so new and exciting. And for example, we have a list of telescopes and how many FRBs they detected within first years in this field. So Parkes detected 23 bursts between 2001 and 2018. Then there are Green Bank telescope, which detected one pulse in 2011. Arecibo detected several Molongo, ASCAP, and CHIME. So ASCAP is part of the square kilometer array pathfinder. So it's a very sensitive antenna. It's also located in Australia. It's ASCAP, so several big dishes that can cooperate and work together or separately. I'll talk about it a bit further in the talk. And I'll focus more on CHIME, this Canadian telescope, which actually made a revolution in the field because being very sensitive and having a big observational area on the sky, it detected, I think, several thousands of FRBs. Well, they published several hundreds, but they have many more in their pipeline. And that's a very recent catalog that they published discussing this population of sources that they found. So we're talking about it later. But you see that large plethora of telescopes is finding fast radio bursts nowadays, and we are very confident that they are cosmological. So even scientists that are looking for actually extraterrestrial intelligence, they are also searching for fast radio bursts because they're exactly looking for such signals which are radio signals strong and in their wavelength regime. And so some of these sensitive telescopes are participating in this SETI program, which is Search for Extraterrestrial Intelligence, as I said. And some of their time is dedicated to surveying stars around us and looking for this radio burst signal. So there are many theories that try to explain radio bursts that are observed, but there is no one that is fully compatible with all the data, and we can just say that's the one. So people are discussing many things. One of the most successful theories is that FRBs are created by magnetars, which are highly magnetized neutron stars, which are also very fastly rotating. So neutron star is a small object, about 20 kilometers diameter, like Chicago or any big city. So it's very small, but it's highly magnetized and 15 Gauss, which is 1,000 trillion times stronger magnetic field than that of the Earth. And its rotation is crazily fast. It can rotate around 100 seconds around its orbit. So they are very weird objects. And if such strong magnetic field gets interrupted and then magnetic lines get reconnected, it can create flares in radio. And so that's the most viable explanation for fast radio burst creation. But there are many other theories, including the extraterrestrial intelligence, aliens, and also black hole progenitors, white dwarfs, some exotic scenarios like axion dark matter, neutron stars, isolated or colliding. So there is 55, 60 different theories, and the number just grows with time. Of course, existing observations with China also disfavor some theories against the others, but we still cannot really say what creates such weird spikes. By now, there is a whole zoo of fast radio bursts. So these are some examples that we have from this is 2019 compilation. So they have different forms and shapes, but the characteristic is that there is a central spike, one or several that are extremely short, milliseconds, and very bright. So they're all like that. The details can vary either due to different properties of the host that create fast radio bursts or environment in which they're embedded, or maybe the propagation of the pulse from when it was created to the observers imprints some differences. So I already mentioned that they're very abundant, and this is just a kind of artistic impression of cosmic web. So the distribution of galaxies around the sky and different bursts going off in different places. So by now we know that there are roughly 1,000 FRBs per entire sky in a day that we can detect. So these are very large numbers. And Chime recently published their updated rate, so it's around 800 per sky per day with Chime in the frequency range. But other telescopes have their constraints, so it varies from different frequency regimes. And these are error bars on the rate of fast radio bursts, but they all are pretty much consistent in that we expect a large number of these events every day. So they're coming on us as we sit here. So how do we know? I mentioned that they are cosmological, coming from large distances, but how do we know exactly? And how can we say if it's something that is created on Earth, in our solar system, in our galaxy, or is it extragalactic? So let's see how do we explain that. And the key is in the dispersion of this pulse. So I will talk about dispersion now, but you can see it here. It's the same pulse detected by Lorimer in 2007. So again, we see from that higher frequencies arrive to the detector later than the lower frequencies. And this diagonal swap through the time frequency diagram shows us that the first pulse is actually dispersed. So dispersion is a very common property. We know that if a light, we just have white light that shines through a prism, the prism will separate different colors, right? And then they will hit out of the glass at different angles, and we will see a rainbow, or just we see a rainbow in the sky, and this is called dispersion. So this happens because different wavelengths will have different speed of propagation in a medium. So in glass, different frequencies will propagate with different speeds, and also they will have different angles of diffraction and reflection in the medium. So that's how we see a rainbow, right? And then that's exactly what happens with radio waves in ionized gas. So we know that between us, Earth, and distant galaxies, there is something called intergalactic medium. So there is gas. Actually, it's not vacuum. It's composed of some atoms. There is matter in it, and this matter is ionized. So ionized gas between the pulse, the source and us, acts as this prism and actually disperses pulses of radio pulses. So in such a way that blue light or shorter wavelengths will arrive earlier than red or longer wavelengths. So this dispersion just changes speed of light in medium, right? And that's how we see that pulse is dispersed. And also by dispersion, we can also measure the distance from which it is arriving, because it will be proportional to the amount of ionized material it goes through. So for those of you who learned integrals, we can calculate what is called dispersion measure by integrating over this cone of ionized gas. So how much ionized atoms there are. So Ne is ionized fraction or density of the gas, and D is the redshift. So we integrate from redshift through the distance where this fast radio burst was created to the observer. Right, and that's how we see that higher wavelengths have lower velocities than lower wavelengths. So today we know the observed FRBs have dispersion measures between 26 to 266 parsecs per square centimeter per cube centimeter to 2,500. And this tells us that such pulses, if you solve this integral, they propagate from high cosmological distances. So they probe universe going back to 3 gigayears to 11 gigayears. So in terms of cosmological redshift, for those of you who know, it's around redshift 3. So when the universe was just few gigayears old. Right, so that's how we know that they are cosmological, and they also travel huge distances to arrive to us from when they were produced. Now some plots. So dispersion measure of this pulses actually, when we compare them to all known sources that were measured in our galaxy, such as just pulsars, what is called other radio sources. So the galactic sources have much smaller dispersion measure because they arrive through a smaller amount of ionized gas compared to what the typical population of fast radio bursts suffers. So this is dispersion measure. Right, so it's dispersion measure divided by the measure of our galaxy to the dispersion measure of pulses. So they are kind of a different population of radio sources than what we have observed before, such as pulsars, which were detected many years earlier. And so because of this dependence, this dispersion of the pulses just gets wider and also so broadened. We can actually measure how much ionized gas is between us and the source, as I said, and we can use it for cosmology. So the amount of gas and how it's ionized and how inhomogeneous it is depends on the cosmological properties of the universe. For example, how many baryons there are compared to dark matter. And this is an example. I will talk about cosmology later. And also we can probe the history of the universe in terms of how ionized the gas was. And we know that very early on, when the universe was very young, most of the gas was neutral, right? And then when stars formed, they ionized the gas. So by plotting this dispersion measure versus distance from us for fast radio bursts, we can in principle see how this ionization properties of gas change with time. Okay, so the observable pulses are very bright, but they also are coming from very large cosmological distances. And so we know that light, when it is emitted far away from us, we will see it dimmer because if you have a source which emits in all directions, the further we are from source, the fewer photons we receive in our detector or eye, right? So the further the source is, the dimmer it is. So we need to divide by the area between us and the source. And so FRB pulses, even though they arrive through these huge cosmological distances, they're still very bright. And that's amazing. And it tells us that intrinsically, at the moment when they were produced, they were extremely bright. So let's see how they compare to known sources, and I'll talk about something that is called light curve, and it's just a measure of luminosity, so how bright the source is as a function of time from the moment the event, such as explosion of star, happened. Right, so this line here is called light curve, and it gives us information about the properties of the sources. So for example, for sun, we know that its luminosity varies with time in a periodical way. For example, this is the luminosity of the sun, how bright it is, as a function of years. So the sun has well-known cycles of 11 years roughly, and it's periodic. Right, sometimes it emits flares and is more active, and then it goes more quiet. So this is a light curve of the sun. We can then look at pulsars. So pulsars are rapidly rotating stars, neutron stars, or white dwarfs that create this very orderly profile of pulses that are very bright and very short. So also these neutron stars rotate with period less than a second. So you have this bright flares on very tiny time scale that are detected. And so this is the light curve of the pulsar. And then if we look at supernovae, which are explosions of the entire star, right? Imagine the whole star exploding. They're extremely bright events because all the energy of the star goes into this explosion and light. The decay over days or years. So at the peak, it's extremely bright, and then it slowly decays. So it's a non-periodic event. It's called cataclysmic event. It happens once the star explodes, and that's it. It's not like rotating pulsar, but it's much more energetic than a pulsar. And some supernovae, for example, Tycho Brahe's supernovae was first detected in 1572, but it still is visible today, so it decays very slowly with time. But if we look at the light curve of fast radio bursts, it's extremely bright and short time and usually non-repeating. Right? So it's very different from other sources that we know. And this is what is called de-dispersed fast radio bursts. So it's when we take into account this effect of dispersion and subtract it out, and so we see all frequencies at the same time. That's how it looks like after the dispersion has been removed. So if we compare energetics of FRBs to the other sources, it can be the luminosity, so instantaneous energy emitted per unit per second can be as bright as of supernovae at its peak, right? So it's for supernovae it's 10 to 36 watts, and for fast radio bursts it also can be 10 to 36 watts roughly. But the duration is much smaller. So supernovae, as I said, are that bright for a year, while fast radio burst is that bright for just milliseconds. So total energy is much smaller, and therefore it's not explosion of a star. It should be something else. But nevertheless, it's very bright and energetic. It's much more energetic than our sun, which is 10 orders of magnitude less bright. So now we want to know more about the sources and find more of them. How do we do that? And most radio telescopes actually have very poor resolution. For example, Parkes has a resolution of the moon on the sky. So even if they detect fast radio bursts, we don't know where it is located within that big beam, right? So with Parkes and similar telescopes, we can detect them in large quantities because they have large field of view, which is also they see big chunk of the sky, but they don't localize FRBs very well. So even if we detect it, we don't know, we cannot point out the galaxy where it is coming from. So it makes it difficult to study the properties of sources of FRBs and the properties of their environments. So that's where Arecibo was very handy because that's a much bigger telescope and it has much better field of view. much better resolution, so it could localize the fast radio burst to a specific galaxy, and that was the first time that we could tell what is the galaxy that the FRB is coming from. We could measure the redshift or distance to the FRB very precisely. With the error bar here is with many zeros after the decimal point. And there were many, so we could localize the FRB relative to the galaxy itself. It was coming from outskirts of the galaxy, not from its center. And it allowed many follow-ups with many different telescopes. So, for example, several different radio telescopes were following it up, such as VLA, very large array, or Effelsberg in Germany. And also different wavelength regimes. So, for example, the XMM Newton, one of these, which is a satellite that absorbs X-ray radiation, Chandra X-ray satellite, and other telescopes were following up the same source to understand better its properties, if it produces different wavelengths or not. And some of them did have counterparts. For example, different radio telescopes could see that, and also it was seen in other wavelength regimes. So this allowed us to study the properties of this fast radio burst better. For example, we could measure the properties of the host galaxy and this relatively small galaxy with stellar mass of 10 to the 7th solar masses. So it's much smaller than our galaxy, and it's more similar to a Magellanic Cloud. It's an actively star-forming galaxy, and also there is a persistent radio source close to this fast radio burst. But this is just one burst, and as I said, some of them repeat, others don't, so there is a huge spread in properties between other different sources. And so just by using this one source, we cannot make conclusions about the entire population and say what are the sources actually. So the one detected by Arecibo is a repeating event, and at that time, so it was 2012, we didn't have any other repeaters on the horizon. There were many non-repeating sources, but only one repeater. And then suddenly in 2019, another repeater was reported, detected by CHIME collaboration, and it had similar properties to the first one. So they all feature this dependent, so they are not as nicely closed as the first event detected. They have some structure, and also in frequency domain, they look like this, and it's called the set trombone effect, because if you make an audio sound of it, it goes down like a trombone when it's played. So this seems to be a characteristic property of repeaters. Most of them feature this scatter in the frequency versus time diagram compared to non-repeating events. And then another localized FRB came also detected by ASCAP array. So this is an array in Australia, and they made a very novel approach to point antennas in different directions. So even though it's an array, the antennas all looked, well, not randomly, but in different directions, so that if you have a burst coming through the field of view of telescope, different antennas would see it at different times. And so they could triangulate and reconstruct where it's coming from. So this actually turned out to be extremely successful, and they could localize several FRBs, even though they were non-repeating. So even for one flare, they could say exactly from which galaxy it's coming from. So this working really great still. And they were able to localize several FRBs, which allowed to study properties of several more galaxies where the sources are coming from. So by now, in total, we know that 18 sources repeat, even though they're non-periodic. most of them, but that's compared to several hundreds of non-repeating FRBs. So apparently non-repeating, we never saw if they repeat or not. We just detected one flare from each. We still don't know if it's subpopulation, if they all come from the same mechanism, and just we were lucky to see these repetitions from 18 sources, or the different population of sources entirely. Recent news, just early in 2021, was that this telescope located in Canada, British Columbia, called Owing. So it came online just maybe a year and a half ago or 2 years ago, and from the beginning, even in the commissioning mode, so even before the pure scientific phase, it started detecting tons of FRBs. So it's really a successful machine for FRBs, even though originally it was designed to do cosmology with hydrogen. So recently they published the first catalog of the FRBs, which ranged from up to redshift 2. So it's cosmological FRBs, but not very distant cosmic events. This was another proof that FRBs are truly cosmological. So if you look at the location of fast radio bursts around sky in the Chime field of view, corrected for its beam structure, so that's the beam of Chime, you see that they indeed come from everywhere around the sky, and they are not correlated to the shape of our galaxy. So they cannot be just coming from galaxies, but they're also coming from places where our galaxy has relatively few stars. And we also see here, if you can see, these triangles are the repeating events, so they also are scattered everywhere around this chart, while blue dots are non-repeating events, and they all populate in this sky more or less uniformly. We also were able, by observing such a large sample, so in first catalog they reported 536 FRBs, 18 of those were repeaters, and 2 were found to be periodic. So they were able to constrain properties, so tell something about the population of repeaters versus non-repeaters. For example, they found that repeaters have much wider bandwidth compared to non-repeaters, so they were found to be broader than non-repeaters. Non-repeaters are narrower, and also they were able to put all FRBs into 4 categories. So one with very narrow pulse and very strong one. Then there is one where there are several pulses, and so on. Okay, so I won't. We were talking about 3 bullet points on a slide. Here's more. I won't read that, but maybe if you're interested, we can talk about it later. So there are several characteristics of different fast radio bursts. And also they found that most of them are either of the first or second category. So when there is only one blue pulse, the two of them comprise of 90% of all detected FRBs. And 10% are in more chaotic variations. So when there are either several pulses or there is a broader pulse with some substructure. So probably this is created by some physical effects around the source. For example, if there is dense medium and the pulse scatters a lot, or something similar, or it goes through another galaxy on the way, that creates structure in the pulse. And they were able to further probe this population of repeaters versus non-repeaters. And I don't think I have much time to go into detail, but it seems that both populations are consistent. So there is a large chance that repeaters and non-repeaters are coming from the same type of sources. It's just some types of properties. For example, they are more, if it's created by magnetars, then the flares are more easily to observe in some cases. or due to the medium around the magnetar that creates these differences. So we still don't know. Then these localizations that I was talking about with ASCAP and other telescopes allow us to study better host galaxies of fast radio bursts. So the properties of these galaxies in which sources of stars that create fast radio bursts are located. And so in this plot, you see green dot is the galaxy, and then white circles are where the FRBs are coming from. And in all cases, it seems that they're coming from the outskirts of galaxies, so not where the population is actually biggest, but from the far away from the center. And so it seems that the FRBs are forming in these gas clouds that are outside of the centers of the galaxies. And also with this bigger ensemble, researchers were able to study properties of these host FRB galaxies and put them in context of broader surveys that they did of galaxies. For example, if you plot star formation rates, or how fast, how many stars in galaxies are forming as we observe them, as a function of the mass of the stars in galaxies. So if you take galaxy and sum up the mass of all the stars, all known galaxies in this survey are gray, so they have pretty high star formation rate, and they're comparable to our galaxy today, or smaller a bit, while the FRBs populate slightly less active star formation rate galaxies. So they're not in the center of this gray bulb where most of the galaxies that we know are located, but they're on the outskirts of it. So they prefer not so star forming galaxies, not so active galaxy types, but quite strong. Another interesting feature is that also scientists were able to plot the amount of oxygen in this galaxy, so how many elements except created in supernovae they are as a function of nitrogen. So it's a measure of the properties of galaxy. For example, normal star forming galaxies lie in this part. Then galaxies with which are called low ionism galaxies are here, and the galaxies with very big supermassive black holes in them are in this part of the chart. And so it seems that all repeaters that are purple are located in normal star forming galaxies, while all non-repeaters are mostly located in these galaxies with low ionization nuclear emission lines. Sorry for technical term, but it seems that galaxies with huge supermassive black holes in them are not so popular in terms of fast radio bursts. So we do have quite a bit of information about both sources and host galaxies, but it's still not enough to pinpoint the nature of these sources. So as I mentioned, one of the most popular scenarios is the magnetar, so rapidly rotating and highly magnetized neutron star. And so there are many mechanisms that are proposed through which such magnetar could create fast radio bursts. That I'm not going into details, but actually there was recently an event located in our galaxy from a magnetar that created a flare similar to fast radio bursts. So this is again a chart of all known radio pulses, and fast radio bursts sit here in blue. Pulsars are this orange line, dots, and then AGN are here, so active galactic nuclei, and normal stars are this yellow dots. So FRBs sit in this blue region, and the galactic magnetar was located here. So it's still a bit 40 times less energetic than the population of FRBs we know, but it's much closer to them than any other radio sources. So we think now that it supports the theory that magnetars are actually create all FRBs FRBs, even though this one is not so energetic, but we were just maybe not liking enough. If you look at it, how this galactic magnetar looks like, the flare from it, it looks exactly by eye like the FRBs that I was showing you earlier. So it's also millisecond, very bright, very narrow, and so it's a good candidate. So that makes theories that involve formation of FRBs through magnetars much more popular and likely. So much time do we have?
Until 8:30. 8:30.
So now I'll talk a bit more what kind of cosmology we can do with fast radio bursts. And they are very unique in that they are very narrow and then they get dispersed by ionized medium, so ionized gas between us and the closed galaxy. And so they can be used as complementary cosmological probes to any other probes that we have so far. And also future telescopes such as Square Kilometre Array, which is located in South Africa and Australia, it's being built. So it will be sensitive enough and have enough bandwidth in radio regime to probe fast radio bursts from very early on in cosmic history, going all the way to redshift around 12, or when the universe was 13 billion years old, which is now 14.8. No, sorry, it will stare back 13 billion years. So it will probe 13 billion years of cosmic history. So for the context, FRBs that we observe today only probe the recent past of our universe, while with telescopes such as Square Kilometre Array, we will be able to look much deeper into the past. So a bit of cosmology to put us all on the same page. So it's been really exciting times, past 20 years to solve for cosmology with telescopes such as Planck, which you can see here. It's a satellite that observes cosmic microwave background radiation. And here you can see the first ever snapshot of cosmic microwave background, which is basically a picture of the baby universe and released radiation from Big Bang. So first it was detected by Hobby satellite in 1992, and then there was a succession of satellites, WMAP in 2003, and then Planck in 2013, that improved measurement of this cosmic microwave background. So I'm not going into the details here, you can ask me later. But by exploring the structure of non-uniformity of this background, we can learn about composition of the universe in terms of what is it made of. And today we know that 70% or so is in a component that is called dark energy, that we also have no idea what it is. It's just we know how it acts on the universe in general, but we don't know what explains it. So it's all this purple on the pie diagram. Then a big portion, around 27% of total energy budget is in form of dark matter, which we also have no idea what it is. So it's another big mystery of our times. We know that it gravitates, so it does pull matter together, but apart from that, we know nothing about it. And that's another 27% of the total energy density in the universe. And then only about 5% is in form of baryons that we all are made of. Right, so we know what happens in this yellow part. So around 5% of total energy, but we have no idea about the rest. But even understanding what's the breakdown here is a big discovery. Now we know that the universe can be roughly explained by this model that is called lambda CDM cosmology, which means lambda stands for this dark energy in its simplest form, invented by actually Einstein. and CDM is called cold dark matter, and it just stands for the blue part on the diagram. Okay, so but Planck probes, they kind of a 2D picture of the universe when it was just very young, shortly after the Big Bang, and it observes this radiation coming from very distant past. But of course, there were many events happening between Big Bang and us. We know that there were stars that first formed, and then first supernova explosions, and then bigger and bigger galaxies were forming, such as ours eventually, and supermassive black holes also formed. And the universe is not empty. Here there is structure, a cosmic web. So it's very rich in events. And today we have many surveys that observe what happens in this universe, but they all only probe our cosmic neighborhood. They are not sensitive enough to go very deep in space. Actually, JWST was James Webb Space Telescope was launched on Christmas Day, and it will be able to probe galaxies at a very distant past. So when the universe was, what is it, maybe 4 billion years old. So that will be our probe of the furthest universe. And it will tell us what happened here, but we still will not have no idea what happened between the CMB and the distant galaxies. So eventually we will have all this complementary information, and also telescopes such as that are now probing, scanning the sky and probing large sample of galaxies. So it's all coming back together. But fast radio bursts will be able to offer a unique way to probe this picture, as I said, because they're sensitive not just to the galaxy itself, they will also probe the entire the composition of the intergalactic medium, what is called, so everything that is between us and the source of this fast radio burst, because they get influenced by all this medium here. So by studying how their dispersion works and how it looks as a function of redshift. So if you have an ensemble of FRBs and make a graph of dispersion measure versus the distance from us, we can then see what kind of cosmology explains this curve and can probe the intergalactic medium of the redshift. So this plot would look like this for the nearby universe. So this is a redshift of the fast radio burst, which is proportional to the distance from between us and the source. And this is dispersion measure. So for FRBs that are not too far away, it just looks like a straight line because it's so ionized. And so if one measures dispersion measure, we can say how far it is, and vice versa. But the slope of this line depends on the underlying cosmology. For example, how fast the universe expands and how dense the gas is in there, and how many baryons there are. And this is potentially a powerful probe because we can then count number of baryons. So how much gas there is between us and the pulse. And can account for what is called missing baryon problem, because we now know that if we just count how many baryons there are in stars, it doesn't amount to this 5% that is seen in the CMB, in cosmic microwave background, and some of the baryons are missing. We don't know where they are. So by plotting this diagram with fast radio bursts, we can check that these baryons indeed sit in this gas that is hard to observe otherwise. So using just 5 radio bursts, there were already papers trying to locate this missing baryons, and they seem to be a very good probe for that. Another thing is that you can study how fast the universe expands, and then that will probe this dark energy component, because it's responsible for, so dark energy is a very weird form of energy. It pulls everything apart, as opposed to gravity that pulls everything together. So we know now that the universe accelerates, right, from the observations of supernovae, so it gets bigger and bigger despite the matter that tries to pull everything together through gravity. So this fast radio burst can actually measure very well, so it seems, how fast the universe expands and then constrain the expansion history. This is graph. Well, so we can also study how the FRBs are length. So if there is a source that produces the FRBs, right, and there is an intervening galaxy between the source and us, then there is a process called gravitational lensing. So we would see instead of one fast radio burst, like mirror picture of it several times. And this can also help us to study cosmology, because you will see same FRB going through different passes because of this lensing effect, and this can also be a probe of the expansion history. Okay. Another very useful property is that we know that this matter between us and the source is non-uniform, because just the gravity pulls together, and so there is what is called cosmic web. So it's non-uniform density, and it's in the form of this walls and filaments, and that's where the missing baryons are. So the fast radio burst, because of its dispersion, can not only probe the total missing baryon fraction, but it can also tell us about the properties of this web. So what is its structure, how it looks like. So it can be sensitive to the actual properties of dark matter, and probe also general relativity, the Einstein theory in the new ways. Another thing is that if you look at very distant fast radio bursts, so 10 million years away from us, they're not observed yet, but why not? They can allow us to probe the history of ionization. So if we live today here, we know that gas around us is fully ionized because stars produce a lot of ionizing photons which break up atoms. But if we go to distant past between Big Bang and us, some of the gas was still neutral. And then if a fast radio burst propagates through neutral gas, it is not dispersed. And it only starts being dispersed when it enters the ionized part, right? And so in this case, if we plot dispersion measure versus redshift, there is a flat part when the gas was neutral for high redshift fast radio bursts, and then there is part when the medium is ionized, so there is dispersion. So by studying how this curve looks like, in case we do observe fast radio bursts from very high redshifts, we can constrain this process of ionization. And this line, so this is a dispersion measure versus redshift, is sensitive to different cosmological parameters in various ways. So it will be able to probe various processes, and I think I'll just skip and here. So we talked about fast radio bursts, which are a new type of radio pulses, very short, very bright, and they're still a mystery. We don't know what they are produced, where they're coming from, except that they're cosmological events. They're very cool and are very promising for cosmology. So thank you for attention.
Thank you, Dr. Anastasia Fialkov, for the interesting talk. Now we'll move on to the questions. If you have a question, please raise your hands. And if the audience online has a question, please put it in the chat. Over there.
With regard to the repeating FRBs, is the definition of repetition just the location on the sky, or is it also about the fingerprint of the radio?
So it's about the same source. So we only can say that it repeats if we know that it's coming directly from the same source. So it's not just from the broader region from the sky, but we know exactly as a galaxy, and so some distant galaxy, and that it's coming from somewhere in this galaxy where we know from. So it's exactly the same source.
The radio fingerprints look the same on the repeat.
They vary, so the shape of the pulse changes.
Right.
In your first plot of the first FRB, it appeared as if the noise level was different before and after the burst. Is that an artifact of the instrumentation, or is the burst affecting things?
So that I'm actually not sure. It's a good question. I would need to
The one with
go.
the multiple FRB signal.
That particular one, the noise looks the same either side.
So this is the same burst.
But when you showed it the first time, like at the beginning of the talk, the levels are different.
Yeah, so I think that's a fact that it's here, it's the dispersed one. And then when you undisperse it, so I'm not sure how, I need to go and check, but it's a great question. But I think this is the picture of this pulse in the dispersed version. You see the dispersion, and this is the same pulse after it's been de-dispersed, right?
The waterfall plot
Yeah, I see.
is still showing the dispersion.
Right, so let's double check. Let's double check. So,
If I may have a second question,
Mhm.
I think from the Chinese catalogue, you've got the number per distance, and it was a peak, I think you said at 2, I'm not sure if it's a redshift of 2 or
Yeah.
2 gigayears.
Mhm.
So that one, so it's peak at 0.5.
Right.
Now, if the peak FRBs are at 0.5, if you want to go further back in time, are you actually going to find those FRBs?
That's a great question. It's still a debate. So one thing is that China is sensitive to low frequencies. So it's, I think, 400 to 800 megahertz. And it's not very as sensitive as other telescopes. So ASCAP is more sensitive, and other telescopes such as Arecibo and FAST are more sensitive, and they do see these up to higher redshifts, so redshift 3. So it might be, and we spoke about that the further sources are the more faint they are, right? Because of the light gets just to divide by the area. So this might be the effect of the sensitivity drops for these more distant FRBs, and also the frequency band, because if FRB is far away, also the frequency redshifts, what it's called, right? Because the universe expands. So from the point when it was emitted to today, if it was emitted at redshift 10 and had a wavelength of 1 gigahertz, so frequency of 1 gigahertz, it will be observed today with a frequency which is 10 times smaller. So even if it's today in the bandwidth of chime, same FRB emitted at redshift 10 might just go out of the band. So there might still be, it's a great question, we don't know, but there might be FRBs at high redshift, and other telescopes are more sensitive to high redshift events.
You have a third question, if I'm allowed.
Yeah.
Others should have a go first.
Do we have more questions? Right, I think you asked your third question.
So you get an estimate of the distance from the dispersion. Isn't that assuming that the dispersion is uniform across the entire distance, whereas the later theories suggest the structure of the universe, you'd expect variable dispersion depending on what the structure.
Yeah, that's also a great question. So yes, this indeed theoretical curves assume first that they assume there are some assumptions about cosmological parameters. So we assume that we know this line, right, black line here, that we know what cosmology is to put in this equation to calculate dispersion measure, and that there are no fluctuations on the way. And if these dots are actually observed FRBs, they are all over the place, basically, partially because there are fluctuations or non-homogeneities in the medium, and also properties of host. So if you have a environment around fast radio burst that is highly ionized, so for example, this magnetar sits in a gas cloud that is ionized, it will also contribute to this diagram, right? So this black line is just cosmological estimate, but in reality there are non-homogeneous medium plus host contribution plus our galaxy also contributes. So it depends if fast radio burst is coming from here and crosses our galaxy in that direction or in that direction. There are different contributions from our galaxy to this dispersion measure. So the idea is that when you on average plot a large population of pulses on this diagram, in average you can recover cosmological line. But exactly for each individual pulse, there are many components that contribute. Thank you.
Right. Do we have more questions in the audience?
I saw the plot you showed of where all of them are described in location seemed fairly uniform. Was there any relation between the redshift for the periodic ones, no, sorry, the repeated ones, or were they also fairly uniform in redshift?
Great question. There is plot in Chen catalog. I don't remember. So it's overall there is a peak at redshift 0.5. So because Chime, so first of all, they see that this fast radio bursts they track, so they are correlated to star formation, right? So there are more of them from regions where there are more stars and less from regions where there are less stars. And same in redshift space, because star formation evolves with redshift. So we know that in very distant past there were no stars and they then suddenly appeared. And then if you plot star formation rate or star formation history as a function of time, there is a peak at around 0.5 or 1 when stars and galaxies were most active, and actually now it's in decline. So that's why there is a peak in fast radio burst that Chime sees, even though it's not super sensitive, as I was just saying. So it sees some subpopulation of very bright FRBs relatively, but there is a tail to redshift 2 because there are bright events out there that it can also detect. And so they have a specific plot that answers your question in the paper, but from what I remember, they trace the same star formation properties. So they also repeaters are related to star formation history. So they prove the same redshift distribution.
Right. If I may ask a question as well. So one of the observations you mentioned was that FRBs tend to come from the outskirts of their host galaxies. Does the theory that the source of the FRBs are magnetars, is this supported by the observation?
There are hundreds of magnetar theories. So some of them are supported, others not, and then they start being disfavored. So yes. Right, and also by this galactic magnetar that we saw, it also supports some of the theories more than others. And so we start putting constraints on the theories.
Right. Do we have more questions from the audience? Right. In that case, I think that will be it for tonight. Thank you once again to Dr. Anastasia Fialkov for giving the wonderful talk, and thank you all for coming tonight. So next week will be our last talk of the term and the year, and we hope to see everyone here again. Thank you and goodbye.
Thank you.